Welcome everyone. So this is our 101st live stream geometry. So we just passed 100 yesterday. So not yesterday, last week. So big milestone, and I'm happy to see everyone on it today. So we're going to go through some more problems from the geometry discussions and problems Discord server. So if you'd like to join us in the future, feel free to email me at mgreenbeta1@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so with that, I will share my screen. One moment. Hold, please. All right, can you all see it? So yeah, sorry, I didn't put the problems in LaTeX yet, but I think it's easy enough to understand. So for this first one, we have a triangle ABC, and X and Y are any two isogonal points on BC. So that's just a fancy way of saying BAX equals CAY. What's the best way to do that? So I could just do this, reflected about the angle bisector. And that's what I think I'm going to do. So here's the angle bisector. I will reflect this segment about it. And it's not what I wanted. Reflect segment AX about the angle bisector. And so this should be point Y. Okay. And O is the circumcenter. Let's see, how do I want to hide the A prime and just show the A. So there we go. Okay. Let's draw the circumcenter. So this is O. The line from X perpendicular to BC. It intersects the bisector of BAC at point W. Okay, so actually the angle bisector that I hid, we actually want to draw it. Let's see, if I move X more this way, it might be a little easier. So this is W. And WO intersects AY at L. So this is kind of a weird diagram. What's the best way to draw this? Probably maybe something like that. Oops. So WO, we want to see where it intersects AY. Yeah, if I change this triangle a little bit, it might make things easier. I don't know if I want to make it like an obtuse triangle or a taller triangle. Let's see what makes a good diagram. So this is L. And we want to show XL passes through the midpoint of arc BC. So there's like a lot of let's draw this point. So this point is the midpoint of arc BC, the smaller arc BC. And thanks for joining, Conry Berry. Good to see you. Okay, so WX is perpendicular. And we have this right here, and then OW and L are collinear. this looks like a harder problem than I originally thought, but because it's really not that simple of a diagram. So maybe it's better if X is on the other side. Like, I wonder if the way I drew it, like it's easier if X is on this side. It's probably true. So what if I go?
It's best to use projective geometry here.
Okay.
So if you draw in the midpoint of that arc BAC, that will be like the reflection of D in O.
Yeah.
Then you'll have a nice harmonic bundle DMO infinity.
Yeah.
And if you would like project that bundle through X, then you will just intersect like XD also with line OW, and you will want to show that it is harmonic.
Okay.
So if you intersect, yeah, DX with OW.
Okay. So let me draw that. Okay. So we want to show that XL and M are linear, right?
Yeah.
And
if that were true, you could project through X. So you project DMO infinity.
Mm-hmm.
So D goes to E, M goes to L, O stays the same, and infinity goes to W since XW is perpendicular to BC. So you want to show that OWEL is harmonic. This is much nicer.
Okay. So we want to show that this is a harmonic bundle. Interesting. All right.
But then you might as well project through D to BC.
Project through D onto BC.
Yeah.
So, okay. So this would go to the midpoint of BC, and then we would have X, and then this point, maybe L, D, and C are linear. I don't know if, no. Let's think about that. So OEWL we want to show as harmonic. Okay, yeah, so you said to project on a BC. Yeah, if we project through D onto BC. So this is the angle bisector. X is kind of like an arbitrary point. F we know is the midpoint, and L would meet at some point here. And it looks like Ryan's joining us. Hey Ryan, thanks for joining. All right, so if we could show X, Y, X, F, H is harmonic, that would solve it. Sorry, GXFH, where G is the foot of the angle bisector. So yeah, we know, so G and F, we know are the foot of the angle bisector and the midpoint of BC. And then we want to show X and H make a harmonic bundle with that. I'm trying to see if I can find like a right angle that I can use. Because one way we could show things are harmonic is by like finding a right angle between two of them, and then like finding an angle bisector. So what if we let AO intersect BC? Oh, then we'd have to let AE intersect BC. Is this the antipode of A? Let's see. I don't think it is. Doesn't, yeah.
Can we use moving points here?
Moving points.
Yeah. Because we just have to show some cross ratio is -1. In other words, harmonic bundle. And stuff like that is pretty nice with projective transformations.
Okay. So yeah, I'm not back with moving points, but it's like you have to show it for 3 cases. So maybe we can move X to be the midpoint, point C and point B or something like that.
Yeah.
Okay. So
I will try to see if we can do it with that.
Okay. But yeah, I like the idea of projecting through D. Because yeah, then we want to show why XGH is harmonic. And the thing with that is, yeah, maybe we could like project onto YXGH back onto the circle, because we know AX and AY are isogonal, right? So that means ID, we know ID equals IDJ. So we want to show IDJ, and this point is harmonic. Maybe it's useful that ID equals DJ.
But this is not true. We need to have a harmonic bundle with F.
Oh, okay. So we want to show
YFXH is harmonic.
Yeah, you're right. It's not G. Yeah. Okay.
Okay, I think we can use moving points.
Okay.
So how that would work? We have this point x, which is a variable,
Mhm.
and we want to show that there exists a projective transformation which sends x to h in this picture.
Okay.
That will basically mean that there is like in other words, that would be like inversion at the midpoint of GF or something like that. Since there is since inversion like makes harmonic bundles. So basically, if we would have yeah, that would be it, but you would need to show it is true for 3 points. Yeah. Okay, so we want to show that there is a projective transformation which sends x to h. There is since ay and ax are isogonal, then there is a projective transformation which sends like a line ax to ay, since this is just like a reflection about the line.
Yeah.
So I think that then the transformation which sends x to y is projective.
Okay.
Also, I don't know if that's really needed at all. Okay, I'm not good at this. I'm just trying. So actually, since x w is perpendicular to BC, then there is a projective transformation which sends x to w, since we have that w is just on the bisector of angle BAC, and this the line xw is never like changing direction, so it is like not an orthogonal projection, but like a projection of line ax onto line AD, which is that bisector. So instead of having that it is orthogonal, it is just like a parallel translation or something. I mean, it's a bit hard to explain.
Okay, so
I used that in the GEO, exactly something like that. So I think it should be all right. So we have a transformation which sends x to w, and L is just a intersection of OW with AL, and when you like project through a point, that would also make a projective transformation, just because it preserves cross ratio. That is like the very basic thing. So I think then we have a transformation which sends x to L, I think. The only problem with that, the possible problem with that, is that line AL changes. It is not fixed when x moves. So I'm not entirely sure. And for point H, you would also have just a projection through D.
okay, I'll be honest, that I don't know as much about moving points, but I think like you're saying, if we do enough projected transformations, then we would end up sending G to H. That's kind of
X to H.
X to H.
Yeah.
Okay. So yeah, Ryan, I actually mentioned this earlier in the session, what Ryan just said, or Ryan told me if we do X on the other side, the diagram might be easier, but then I'd have to redraw the whole thing. So yeah, let's see if we can just do it looking like this for now. So, okay, so we want to show O, E, W, and L are harmonic. which after you project through D, that's the same as saying that F, X, G, and H are harmonic. So an X and G is kind of fixed and F is kind of fixed. So if we show there's a projected transformation that takes X to H, then we could solve the problem using moving points. That's what you're trying to show, right?
Yeah,
Okay.
but maybe it's better to not use it since I'm not so good at it, and like I wouldn't even know if we made a mistake.
Yeah, let's see if we can show this is harmonic without moving points just for the time being. Yeah, let's spend another, maybe 5 minutes, see if there's another way. Oh, Brian says he thinks he solved the problem, but it doesn't work with the way I drew it. So his solution would work if X is on this side and Y is on the other side. So you guys want to redraw the figure? Or I wonder if there's a, I think I'd have to redraw it, because the moment I move X to this side, then the diagram just doesn't work. Are you guys okay if I redraw it the other way?
Yeah, my drawing is also has X on the left.
Okay, all right, so let's do that. I'm gonna delete a bunch of stuff. All right. Let's see. So I could draw this, it's just it has to be a ray. This is X prime. And we have this ray. All right. And then we've like drawn the segment twice. So, okay. The line from X perpendicular to BC, we want to see where that meets the bisector. W. Let's draw this point also. WO intersects AY at L. That does make the diagram look a lot easier. And we just, this diagram does look way easier, doesn't it? We want to show that XL and M are collinear. All right. So we can draw this. And I forgot what we even were doing before. So we wanted to show that, so MO and D were harmonic. MOD infinity is harmonic, and we want to project through W, right? So from W, let the parallel to AO cut AY at G. Okay. So this is point G, and you're saying WXG is isosceles. That's interesting. Do a homothenity with WXG and OAM. Okay, so you're saying OAM and WXG are homothetic. So that would mean, let's see what the, so they're like inversely homothetic, so X would go to M, is that right? Okay, if we can show that, then basically that would mean that those three concur at L. That's pretty interesting. Okay. So if we show WXG as isosceles, then by a homothenity at L, and the left and the are just angle chasing. Okay, so WXG we can show that's isosceles by angle chase. And OAM is obviously isosceles. So interesting. All right. Okay. So we want to show WXG is AOM. Or I think you mean XWG. And we have a very like symmetric figure. This is like the angle bisector of XAY. So this WG we defined it to be parallel to AO. WX we know is perpendicular. So yeah, we know that this angle is equal to this angle just because WX is parallel to this and WG is parallel to this. So XWG is AOM, we know that. And yeah, where do we go from there? How do we know W? Let's see. Yeah, I guess it should all be okay. So how do you like I understand that XWG equals AOM. How do you prove any of the other angles? Let's see. Since DWG equals DAO equals DWX. So yeah, I understand it. So this is an angle bisector. Then XAW is GAW. Okay. AW equals AW. Okay. So these two triangles, like I understand that this is the angle bisector. WG. So this bisects this angle and this angle. Well, okay, if we know it bisects this angle, then that basically solves the problem. Okay, so XAW is GAW, AW equals AW. But do we know AX equals AG? So basically you're saying XAW and GAW are congruent. Like we're trying to show that those are congruent, right? But so I know that these angles are equal, and I know that AW equals AW. But is there another angle I can show as equal? DWG, oh, okay, DWG equals DAO, and then, oh, because this is perpendicular, it's just an angle chase. Okay, all right. So yeah, it is, yes, okay. I got a little confused. All right. So that looks like it solves it. So let the parallel to AO through W intersect AY at G. Okay. Then, so WG is parallel to AO, WX is parallel to MO. And that means that angle XWG is angle AOM. All right. That's step one. Step two, we show that basically WD is an angle bisector of this. So which that means AWX and AWG would be congruent because we know that this, okay. So angle DWG is angle DAO. Which we can then calculate is equal to this angle. I think that's so DAO is DWX because so DAO is DAH. Where H is the orthocenter, so I'll write that later. So, which is DWX. And that's because the orthocenter and the circumcenter are isogonal conjugates. So yeah, so that's okay. So once we know that, that means that AWX equals angle AWG. And that means that AWX is congruent to AWG. And that implies WXG is isosceles. And homothetic to triangle MAO. So that means that WO, AG, and XM concur at the center of homophoity L, which means that XM passes, which means that XL passes through the midpoint of our BAC. All right, let's move on to the next one. So yeah, this is a really elegant way of doing it. I'm sure moving points, there's a way to do that too, the way we had it. But yeah, this seems a little bit simpler. So yeah, the more tools you know in geometry, sometimes you can really quickly see solutions to problems that are longer, but because you know the tool and you know how to apply it, you could solve it faster. So that's kind of an example of that. All right, so let ABC be a triangle with M is the midpoint of BC and O is the circumcenter. There's M and O is the circumcenter. This almost looks like a right triangle, but it's not. There we go. So we have O, and B lies on the circle so that AB is parallel to BC. And Z lies on it so that AZ is perpendicular to AM. So that is Z. Okay. W lies on AM, so that OW is perpendicular to ZB. That's kind of weird, but okay. So we'll draw the perpendicular to ZB. Whoops, not that, but this. And I'll make it look a little better in just a second. And we want to show that OD is tangent to the circle OW now. So how do I get W to look a little better? Maybe that's okay. All right. Let's draw this. So this is going to be the midpoint of ZB. It's perpendicular. And we want to draw OWM. And we want to show OD is tangent to it. Okay. So we want to use that this is a right angle. I could draw. So yeah, we have a cyclic quad here, right? Because this is a right angle and that's a right angle. All right, but this is also a right angle, O and C. So maybe it's worth drawing this point, and if we can show OWF is a right angle, that would be a way to solve the problem. Well, not really. We know OWF is right. We want to show that this is tangent. So WF is parallel to ZB. Interesting. I wonder if this point, well, we know this is a right angle, but I wonder if it's like parallel. I don't think it is. So we could try to show angle DOW is like 180 minus OMW. But DOW, so yeah, another way we could try to show angle ZOE. If we can show ZOE equals OMW, would that solve it? I think it might. I think the problem might be equivalent to that. Oops, let me do it the right way. ZOE and then OMW. Yep. So yeah, I think the problem is equivalent to that. And OMW is just OMA.
So basically, like angle ZOE, it's gonna be the same as ZOE prime, where E prime is on the circle.
Okay.
So OE meets E prime in E prime the circle, and
Make it E prime.
yeah. So the way I like this is because now we have to like show something about equivalence of arcs on a circle, and maybe we can even use Archimedes, but I'm not sure.
Archimedes lemma.
Yeah, but I think that is like an extra thing to work. So no.
All right, I'll leave it there for now, just to see. So yeah, AMO is 90 minus AMB, obviously. So maybe it's easier to think about it like that. So AMB is like, we want to show as OZB. That's kind of interesting.
Yeah, but then OZD is good because OZ and AM meet on the circumcircle.
Oh. OZ and AM meet on the circumcircle because it's a right angle. Okay. That is a good point.
And now we are clearly done because then GZD is equal to GAD is equal to AMB because of the parallelity.
Ah, very nice. All right, so we've solved it. Very cool. Okay, so since angle ZA, so we don't need this circle really, and we'll keep that circle. So since ZAM equals 90, that means that AM and ZO meet at a point G on the circle. All right. See if that what that does. No, it didn't fix it. I have to do 2 backslashes. Oh. Why does it do that? Okay, you know what? I'll just do it like this. And see if this works. I think I gotta do this. That. There we go. And then so yeah, we know OZD is isosceles. So yeah, I don't even know if we need point E really. I don't think we do. So yeah, let's write this out. So we have angle GZD angle ODZ. So ODZ equals angle OZD is angle GZD, which is angle GAD, which is angle AMB. Okay. And so then angle DOM is, well, yeah, what was I doing here?
Well, maybe we do need E.
Well, maybe we do need E. Okay. Okay, so we wanted to find angle DOM. And what did I say about DOM? It's like DOG. I had a simpler way of doing DOM. I forget what I was doing.
Yeah, so we know that OMW equals to EOD because they are both 90 minus equal angles, and that is the same as the tangency.
Oh, okay. OMW is equal to EOD. That's what we want to show. Okay.
Yes, we know that from the angle equalities, and also EO and W are collinear. Yeah.
Okay. OW is perpendicular to ZD. Okay, so let E be the midpoint of ZD. Then E, O, and W are collinear. Okay, so yeah, so if we could show EOD equals OMW, that's equivalent to the tangency. Okay, so so angle EOD is 90 minus angle ODZ, which is 90 minus angle AMB, which is angle WMO. And this means that OD is tangent. All right. Very cool. All right, let's try a harder problem now. So one of the riddles and see where we can get. This is a middle riddle. This is also a middle riddle. This one looks kind of interesting. So we have the 9-point center and this median point. Yeah, let's try this one. So all right. So what's the best way to draw this median point? Should I draw all the tangencies or I'll do it that way. So the tangents at A, B, and C, see where they all intersect. Yeah, it makes the diagram a little bigger, that's the thing, but I think it's worth it. So you have all these tangencies, and ABC is like the end circle of this triangle, and it's basically the Gergonne point of this triangle. So I'm gonna have to rename some of the points, but so this is L. And OL intersects BC at D. And we already have a D, so I'll redraw, I'll rename stuff. So this is point D. I think we did another problem recently with a point with the line OL. So OL, I think it's the radical axis of the three Apollonius circles, right? I think that's what we said on a previous session. So the line from D perpendicular to AD. We want to see where that meets AB and AC. So one of those sides we're probably going to have to extend. Yeah, it's tricky. So yeah, picture might not look perfect, but let's see. ABC almost looks isosceles. Yeah, I don't want L to be that close to O. But then I don't want AD to look like an altitude either. So just trying to figure out the best way to do this. What if I make it like a really, if I do it like this? No, yeah, I don't want to make it super obtuse. If I make it super acute, I'll just do something like this. It's not perfect, but oh well. So I need to draw this point. There we go. And then this point. X and Y. So this should be X and this should be Y. Then we have the 9-point center of AXY. Well, Okay, let me hide a bunch of stuff. But apparently A, L, and N are here. Okay. And it almost looks like this passes through that. So I'm going to check whether or not it's true. All right. So we have this, this, and this. And then we have this. OL intersects BC and D. I think that's the diagram we want. And then we want the 9-point center. That point. And it almost looks like it lies on, I mean, the 9-point center doesn't lie on this median necessarily, so that is just a coincidence. Wait. Why does it look like I lies on AG? I is not supposed to be. That's weird. The 9 points. Oh, yeah, because it's AXY, not ABC. So yeah, first of all, I guess step one is to show that the 9-point center of AXY lies on the A median of ABC. That is very random. But the 9-point center, yeah, it's isogonal to the cos theta point. And that's a little tricky to draw, so. Okay, so I don't think AD and H are collinear. Like I thought they were, but now I see they're not. So this, instead of I should call it N. So yeah, oh sorry, that is the problem. That's not just something I noticed. The problem is to show N lies on the A median. Which is the same as saying that if M is the midpoint of BC, then we want to show M passes through, AM passes through the cos theta point of AXY, which I don't know how helpful that really is. But. I'm going to keep trying to draw a better figure. Sorry, this just bugs me a little bit. Let's see. I don't know if it's going to get too much better. I think it was better before. Okay. So OL is the radical axis of the 3 Apollonius circles. Although I feel like drawing in those will make the problem super messy. So D has the same power with respect to all the Apollonius circles. One sec, guys, I'll be right back. All right, thanks for waiting. So the 9-point center of AXY, what can we say about that? AB is the altitude. So the 9-point circle is going to pass through B. So it's going to pass through the midpoint of XY. Not sure what we can say about that. DI and DNI is isosceles. And then let's draw the circumcenter of AXY. So it's J. And let's draw the 9-point circle. So it would be that. Anything special about point K? Well, K, N, and I are going to be collinear. That's so homophily about N with ratio 2. We'll take that circle to AXY. Can we say anything else? I guess another way of phrasing it is we want to show if AM meets this at M, we want to show ABMC is harmonic. Let's see. Maybe we could define N some other way and then show that that's the 9-point center. I kind of like that better. I just don't know how we define N. I guess what we could do is we could let the perpendicular bisector of BI meet a G at N, and then we could try to show that's the 9-point center.
Suppose that like H is already taken, then like J prime is the orthocenter of AXY. We want to show that J and J prime are the same distance from AG.
Okay, so we want to draw the orthocenter of AXY. So let me think about that. So I'll just draw it like this. So P. Then what were you saying?
We would like to show the distance of P from the line AG is the same as J from the line AG.
Okay, that P and J are the same distance from AG. Interesting. Hey Nguyen, thanks for joining. So this is our third problem. It looks like the hardest probably.
Is it true that JL is perpendicular to AG?
That JL is perpendicular to AG?
I wonder.
I don't think so. It looks just slightly,
No.
yeah. But it's an interesting idea. But basically that means we're saying J and P are like isogonal conjugates. So the orthocenter, well, yeah. So J, N, and P, we know that J. Okay, so you're saying it's the same as showing the distance from J to AG and P to AG. I see what you're saying. Hello. So we know AP and AJ are isogonal. We need to show that so basically we need to show that like AG is a median of triangle APJ. That's another way to say it. Because yeah, the midpoint of PJ is N. We need to show that that's a median. Yeah, what if we let AJ? I wonder. I don't think these concur. But maybe we can still say something else about AJ. If I draw this circle, we want to show this as a median. We know it passes through M. I keep getting confused. So oh, because I keep thinking M is the midpoint of ArcBC. It's not. It's the point that makes it harmonic. Okay. We call this Z. So I don't get confused. Sorry.
Are OD and H on a line?
Oh, what?
Are O, D, and H on a common line?
No, I thought they were before. That's one of the things I thought, but if you move the figure, you find out that they're not. So, like, this makes it look like it's close, but I think I showed it before where they were like farther off. Let's see. I guess I'll just zoom. Yeah, like if you, yeah, and misses it just barely. Like if I draw HD, yeah, there you can see they're different. Let me get my phone. All right.
Could you draw in line AG, AJ?
AJ.
No, AJ.
Oh, AJ. Yeah, these don't actually meet on the circle. It looks like they do, but yeah. But was that what you were wondering, or did you have some other idea?
Yeah, it was.
Okay. We think alike. Yeah. yeah, we want to show AG is the median of APJ. And yeah, like you said, that's the same as showing the distance from P to AG is the distance from J to AG. Yeah, this looks like a hard problem. We could try for another like 15 minutes maybe, but yeah, it doesn't look easy. Yeah, Kn and I are collinear. We know that. What do we know about the 9-point circle? 9-point center. Let's think about this. So we want to show that the asymedian of ABC is the A median of APJ. So that's basically the same as saying that. I wonder if that means. Well, yeah, I mean, it's just the same as saying we want to show angle IAY is angle BAN. Is that right? No, I don't think so. It's the same as showing we need to draw the midpoint of BC. And I don't think OM and Z are actually collinear. I don't think OM and G are collinear. That's a good thing. So but that just makes things a little messy, so I'll hide it. So L is the in-center of FEG. So we want to show an in-center. Yeah, let's think about it a little differently. We have triangle FEG. L is the in-center and A is the point of tangency. And we want to show that that line AL passes through N. Okay.
Are points B, O, J, C concyclic?
B, O, J, C. No. B, O, C, G is. So yeah, I don't even know if it's worth drawing, like, because we know, I'm just trying to make the diagram look a little nicer. But we know that this is the in circle of EFG. And L is the center of that circle. So let's think about this. We want to show the centers of two circles are collinear with a point A. I wonder what the radical axis of those circles are. So we have this one. And is the center of this circle. And then we have this, L is the center of this circle. So LN is the line connecting the centers of those circles. That's weird because the line connecting the centers is supposed to be perpendicular to the radical axis, but this, what am I missing here? No, L is not the center. Oh, L is the Jirgan point. Okay, so L isn't the in center. So yeah, we really do have to draw those two. What do we know about the Jirgan point?
I wonder if AJP is a right angle.
AJP. I would be surprised, but I can check it. It's close, but yeah, 86.72. Because yeah, if AJP was a right angle, like yeah, J is the circumcenter of AXY and P is the orthocenter. So that would mean like, yeah, that would be yeah. But it's an interesting idea. I don't think that's actually collinear. No.
I wonder if AM is the symmedian of triangle APJ.
If AM is a symmedian?
Yeah, actually, we do know that that's if the problem is true.
Okay. So yeah, if the problem is true, then AMJ would be a symmedian. Is what you're saying. So because yeah, AM and AG are isogonal. Yeah, if the problem is true, that would be true.
In fact, it's sufficient to show this.
Yeah. Yeah, I kind of like that. So we want to, that's a good way to phrase it. We want to show AM as a symmedian of APJ. And I wonder if, does MP equal MJ? I don't think so. It doesn't, but I'll check. I wonder if we draw the tangents at P and J. See where they meet. Interesting.
It's surprising.
Oh, sorry, I was thinking, if we draw the tangent to APJ, then it's the same as showing that this line, AP, AM, and AJ form a harmonic bundle. But what were you saying?
I find it surprising that in this problem the Humpty and Dumpty points haven't come up yet. It would be very natural to like some of the points to correlate to them.
Yeah. Oh, it is interesting. Yeah, I'm not sure. Okay, so yeah, we want to, if we can show that this and then AM and then this tangent are harmonic, that would solve it. So AJ is the center of this circle. Maybe we could project onto this circle somehow. So AP would go to the reflection P over XY. So AP and AJ would go to 2 points that are like parallel to XY. Is this parallel? Is this line parallel to XY? Let's see. No. I wonder if there's something special about this point. Q. Now I'm just kind of making it more complicated. All right, let's work on this for maybe 5 more minutes and then we can switch to another problem. I'll just try that one more time. So I'll draw that tangent to APJ. And I want to see where it meets this circle. Is there anything special about point Q? Maybe is QJ really tangent to that circle? I mean, there's a lot of things that look almost true. Let's see. No, it's not. And then QM I don't think that's really concurrent though, even though it looks like it. No, it's not. And then Q, I, and Z, I don't think those are really collinear. So QK tangent to that circle. It almost looks true. Oh, but you can see it's not true there. So yeah, I don't know if we can really do much with point Q. I like the idea of using harmonics, but I just don't know if it'll work here. All right, let's move on to the next problem. I feel like we've spent a while on this one. So this one like uses a similar idea. Let's try this one. So we have a triangle ABC and M is the midpoint. BC.